Relationship between Kc and Kp. In this video, we're going to use the ideal gas law to relate Kc and Kp together. We'll derive a general formula for this relation so that we can use it for all situations. And then we'll do a couple of examples, one where we calculate Kc from Kp, and then another that shows how the quantities are related when the moles of gas doesn't change. Now that we've talked about Kc and Kp, it would be nice to have an equation that relates the two for the gases. Now, of course, we could go through each time and convert the pressures to concentrations of every species in the reaction, and then fill those concentrations into Kc. But that's a lot of work. We can do this for the most generic case once, and then we'll have a simple equation to do the relation for us. First, let's think about how we would convert pressure to concentration, or the reverse. The equation that allows us to do this is the ideal gas law, or PV equals nRT. Concentration equals moles per liter, so we need to rearrange the equation in a way that gives us this. So let's rearrange it this way. Now let's make extra clear that the N over V is what we're looking for, so that we'll have moles over liters. So we'll rearrange this one more time, and we'll pull out the N over V terms. So this is our moles per liter, or our concentration. And we'll use this in the next slide. Now let's start with Kp and see if we can find a way to relate this to Kc. So let's take a simple chemical equation to start with. Simply A goes to B. We'll even say that we don't know the stoichiometric coefficients to keep it as general as possible for the moment. Now let's write Kp. Keeping in mind what we did on the previous slide, we can fill in the ideal gas law. Now let's rearrange a little bit. We'll pull out the concentration terms, or the N over V. Now, what is this concentration B over A, where it's raised to its coefficient terms? Well, you may recognize this as Kc, so let's pull that out. Now, the RT terms are left over, and you'll notice we have it raised to this delta N. This is because it's going to change a bit based on what the total number of moles on each side of the equation are. You have RT on the top, and that's going to be raised to the total number of product moles, and RT on the bottom, which is raised to the total number of reactant moles. So if we take the product moles and we subtract the reactant moles, that will be what we need to raise RT to. So delta N is the difference in moles of the gas between the products and the reactant. Now let's do an example. So you may recognize this from the previous video that we watched, where we found Kp, both in equation form, and then used some numbers to fill in and solve for Kp. Now that we have this relation between Kc and Kp, we can also calculate Kc. So let's fill this in to the equation we found in the previous slide. So if we're solving for Kc, we'll solve this equation for Kc. I usually recommend rearranging the equation first and then solving, then putting in the numbers. So we fill in our numbers, and we end up with 21.346. Now, things to notice. First of all, remember when we fill this in, we are actually filling in a unitless quantity, and so our Kp is unitless, or Kc is unitless, just like our Kp was. You'll also notice that this is a -1, because we're filling in 0 moles of gas on this side, subtract 1 moles of gas on this side. We don't include the solids in this calculation, simply the moles of gas. So it is 0 moles on this side, 1 mole on this side, so 0 minus 1 is -1. Now, another sort of example that I would like to do, I would like us to derive a formula that is true if the number of moles of gas on one side of the equation is equal to the number of moles of gas on the other side of the equation. So let's think about this a moment. If the moles of gas are the same, what is delta N? Well, if we would have, say, 2 on one side and 2 on the other, our delta N would be 0. 3 on one, 3 on the other, delta N would equal 0. So no matter what we have, as long as they're the same on both sides, delta N equals 0. Which RT raised to the 0th power would simply be 1. And therefore, Kp is equal to Kc if the moles of gas on each side are equal. So this is a useful thing to keep in mind to save yourself some time if you notice that the moles of gas on each side are equal.